It says right there. All right. So here's what's going to help you a great deal when you're looking at a test. By the way, tomorrow's test, you can't be slow. Tomorrow's test, you can't sit there and say, what's the formula for calcium chloride? You know, we have to be getting a little faster at that. You get that? And so you have to be, if I say, let's do the net ionic equation, you can't sit there and take 5 minutes to do that question. You get that? That's way too long to do. And I showed you a shortcut, right? So if you're doing a shortcut for net ionic, you shouldn't be taking that long. Now, some of these also, I'll have one where you have to do like all of this. You show this equation here, you show the Leo half reaction, and you show the GER half reaction. I'll make you do that once, and then there'll have to be multiple choice questions based on this idea. You get that? So same thing with ionic, net ionic, complete ionic. I'll make you do the complete ionic equation and the net once. And then the rest of them are multiple choice questions based on that, and that's when you'd want to use shortcut. I'm looking at your faces. Does that make sense to you, what I'm saying? Are you thinking about snow today? Or okay, you're right. All right, so let's go over here. Here's where your mind should work. And nobody taught this to me in high school. I didn't even understand it. Nobody taught this to me. I just eventually figured it out. But of the 5 kinds of reactions that you already know about, one of them is called double replacement. But how many kinds of double replacements are there? Remember the precipitation one? That's where you use the chart. You look up is it soluble, insoluble? And that's where you have the net ionic equation. Remember that? And the same thing here. You can have a net ionic equation here, but if it's double replacement, it's either the driving force is either the formation of a solid, that's a precipitate, and that's why it's called precipitation reaction, or acid-base neutralization, meaning you formed water. Now, why did I draw a line here? I drew a line here because that has its own driving force, and so does that. But all 4 of these, have a completely different reason why they occur. And they occur because somebody's going to lose electrons and somebody's going to gain exactly the same time. There's no delay. It's not like I'm going to lose 2 and I'll just wait around. No. You can't lose 2 unless somebody gains 2 at the same time. Get that? And that's called oxidation reduction reactions. Now, so here's your vocabulary word. Anytime any chemical loses electrons, if it loses electrons, we say it got oxidized or oxidation took place. Now, my memory trick is LEO, and that is Leo. Leo the lion says GER. And so I know that Leo the lion says GER. If you gain electrons, you are being reduced. Okay, so the kind of questions on the test would say, who gets oxidized in this reaction? Oh, oxidized? Oh, you mean who lost negative electrons? And if you lose negative electrons, what does that mean? If you lose negative electrons, what does that mean? You become more positive. Think about the number line. If you go from here going that way, you became more positive. You're going that way, you became more negative. Okay, so anyway, even though the official name is oxidation reduction reactions, I'm sure this is where they came up with this little abbreviated name, redox. Redox is reduction oxidation, or oxidation reduction. All right, so let me see, I'm gonna go over the same one we did before. The rules are kind of simple. They're kind of simple. The first thing you do, you write out the balance equation. You say, well, I know how to do that. We did that last chapter. So check, I got that. Assign oxidation numbers. You say, how do we assign oxidation numbers? Okay, number 1, if an element is not combined with any other element, then give him a 0. This chlorine is not combined with another element, so give him a 0. But what's the oxidation state of sodium in sodium chloride? And that's the same way we did that chapter where we wrote formulas. You're +1 and you're -1. Now, do you notice that just glancing here, do you notice that somebody's changing charges? How do you change charge in chemistry? I either gain electrons or I lose. You must be redox. It has to be redox. And I promise you, look right here, nobody in these, nobody changes charges in a double replacement reaction. Nobody. It's not redox. Got it? The only one that's not redox is double replacement. Now, so we go over here, and we notice that we're going to do these things called half reactions, and I made this up. It works. It works very well. It's not in your book, but what I do is I'll do it all over again. I look to see who got LEO'd. I just made that up too. All right, and LEO'd means who lost electrons and became more positive. Well, let's take a look. Sodium became more positive, didn't it? So I'm going to put Na. So here's what we did yesterday. I wrote Na, 0, and then I drew an arrow. I said, what happened to Na, 0? What happened to you? Well, look over here. You can see what happened to me. I turned into an Na+1 ion. You did? How? How do you go to 0? How do you go from 0 to +1? Well, I also threw away one of my electrons. I lost one of my electrons. And that's what we did yesterday. Now, then we came down here and we said, well, who gained electrons? Who gained negative electrons and became more negative? And you said, well, chlorine went from 0 to -1. That's you. So what I did is I drew a single chlorine, and the chlorine started out as 0, and I left a little space here, and I know that chlorine turned into what? Chlorine 0 turned into chlorine -1. Well, how do you do that? How do you go from 0 to -1? Well, I grabbed a hold of an electron. I grabbed a hold of a negative electron, and that threw me down to -1. Now, the only thing that didn't make sense were the numbers, right? So now I'm going to go back and fix the numbers. Look up here. Did you only start with 1 sodium? No. I started with how many? 2. Wait, you said each sodium had to lose 1 electron, but now you're telling me you have 2 sodiums? So you must have lost a total of 2 electrons. Okay, I can do that. And did you start with 2 sodiums? You only ended up with 1 sodium ion? No. I ended with 2 sodium ions. And again, we don't reduce half reactions because that's only half the story. It's only half the story. We don't reduce it. Down here, chlorine. Hey, chlorine. Did you only start with 1 of you? Nope. Now, I'm not 2 chlorine ions. I'm actually diatomic chlorine. Everybody get that? That's not chlorine ions. These are. And I ended up with what? 2 what? 2 chloride ions, right? But how'd you do that? I think you said each chlorine had to gain 1 electron. Now you have 2 chlorines, so okay. And then you always check to see if the electrons match. If I lost 2 electrons, you had to gain 2. They have to match. All right, so we did that. Then we did another one. So I tried to prove to you that synthesis really was redox. It's still synthesis, but the driving force is redox, isn't it? Then we did another one. Prove to me that single replacement is redox. Well, we did this one. Zinc plus hydrochloric acid yields hydrogen gas and zinc chloride. Okay, good. Now what? Balance the equation. Whoop, I got that. Oh, you're not combining with anybody? I'm going to give you a 0. I'm going to give you a 0. That was easy. And what about in a compound? +1, -1. +2, -1. Okay, who got LEO'd? Let me ask the people who weren't here. If the people who weren't here can answer this question, then shame on you if you were here. All right, Jonathan, who lost negative electrons and became more positive in this one? Who became more positive in this one? Go loud. Zinc? Yes. Okay, so zinc went from 0 all the way, jumped up to +2, didn't it? How do you do that? How does zinc go from 0 all the way up to, how did it go from 0 all the way to +2? And I got rid of 2 of my electrons. That's how I did it. And by the way, when you do the LEO, put the electrons on the right. When you do the GER, put them on the left. Is that easy for you to remember that? All right, now, who then, watch this now, Ramos. We know that zinc got more positive, but who got reduced? Who gained electrons and got reduced? Who got more negative? Look at that, scan through here, who got more negative? I'll give you a clue. Zinc went from 0 to +1, not you. Chlorine went from -1 to -1, and nothing. They didn't do it. So I got one more. What is it? Yep. And hydrogen went from +1 to what? Down to 0. So how did this hydrogen who was +1, how did he turn into hydrogen with a 0 oxidation state? Everybody look up here. How does that happen? How do you go from +1 down to 0? I must have gained a negative electron. See that? See, if I was +1 and you threw an extra electron, I'm going to jump down to 0. See that? Now, the only thing that doesn't make sense here are the numbers, right? So we go back up here and look at the numbers. Did you just start with one hydrogen? Nope. I started with 2 hydrogen ions. Yeah? Then that means you need to gain 2 electrons. And how did you end up here? It's not 2 hydrogen ions. What is it? It's actually diatomic hydrogen. Now, we check again. You lost 2, you gained 2, they match. All right, what I'm going to do, I'm going to give you another one. And if you can do this by yourself, so I don't know if we did this yesterday or not. Did we do aluminum and iron oxide yesterday? Oh, we did? Okay, so you already know that one. All right, let's see. I got one. Prove to me that the decomposition of water is a redox reaction. Let's do that. The decomposition of water. The decomposition of water. Prove to me that that is a redox reaction. Do the Leo half reaction. Do the Gur half reaction. Does everybody know what water decomposes into? It decomposes into elements, only elements, so does everybody know that's going to decompose into hydrogen gas and what else? Okay, everybody got that far? Okay. We're going to balance it, aren't we? Boink. And boink. Well, that wasn't too bad. Now we have to assign oxidation numbers. And really, if you could do the last 3 that we've done, if you do those last 3, you're not going to have that much trouble at all. I think the hardest thing is to remember, what does Leo mean? Lose negative electrons, you become oxidized. But if you lose negative electrons, you become more positive. That's what you have to remember. All right. How about somebody who's not 100%? I'm not 100%. Just raise your hand. I'll walk you through it, and you'll feel a lot better about it. Who can say, I am not 100% on this? All right, ready? So we'll walk you through it. Leo means lose negative electrons and become more positive. Did anybody become more positive here? Remember the number line? -3, -2, -1, 0, 1, 2, 3. Did anybody go that way on the number line? Say that again? I'm sorry. No? Okay. Hydrogen went from +1 and dropped down to what? 0? What did oxygen do? He went from -2 to 0, didn't he? That's actually becoming more positive. Okay, so who got Leo'd? Right? So now, what I do is I draw one atom at a time, and then I'll fix the numbers later, okay? Each oxygen started at -2. Now remember, Leo, I'm going to put electrons over anyway. Each oxygen started as -2, but each oxygen ended up as 0. How in the world can you do that? How can you be -2 and now all of a sudden you're not -2? And you had to give away what? What do you have to give away? How many electrons? If you went from -2 to 0, how many negative electrons did you have to give away? 2. See that? Now, let's go down here and tell me who got GERD, who got reduced? Who gained negative electrons and become more negative? Who became more negative? Probably, because that's the only one left. Each hydrogen started out as +1, leave a space, and each hydrogen ended up as 0. Now, how is that happening? How can you go from +1 and drop down to 0? How many electrons would that take? So you'd have to gain 1 negative electron. Now, we're okay except for the numbers, aren't we? Is that okay? Has everybody got at least a story of who got Leo and who got GERD? Okay. All right, so go back up here. What form was this oxygen in? I actually had 2 oxygen -2, didn't I? I really had 2 of those. And what form did it end up as? Didn't I end up as actually diatomic that? So you said each oxygen had to lose 2, but you have 2 of them now. I got to change that to a 4 then, don't I? All right, now, go over here. Let's go back to Noah again. Noah, you help me out on this one. How many of these did you start out with? Okay, you're right. You're right. But each of them had to gain 1. Now you're telling me you have 4 of them, so that's going to be a 4 there, right? And then what about this? How did it end up? Did it end up as hydrogen ions, or it really was 2 H2s, wasn't it? Isn't that what it says? Now, and here we go. Ooh, yeah, that's good. That's good. They match, don't they? Now, the question I had yesterday, and I had somebody come up here, and I gave them some fake dollars, but the question, I'll even tell you the question tomorrow. It's going to sound very much like this. In this reaction, what was the total number of electrons that were transferred? And because you've been in school so long, and somebody says total, and you say 4 and 4, you're going to say 8. That'd be wrong. What's the total number of electrons that were transferred? 4. The same 4 that I lost are the same 4 that you gained. Isn't that right? What do you think? Is that a little bit? How about today? Was that a little easier today? They've heard it twice now. You've only heard it once. So, yes.
I have a question about the subscript with the hydrogen gas. When we did zinc and hydrochloric acid yesterday.
Okay, wait a minute.
I think.
This one?
Yeah.
Okay.
Oh, never mind. I just didn't write it down correctly.
Right. So this really is in the form of an H+1 ion, isn't it? But this is not. It's non-ion. Good question. Yes.
How come on this side you combine the subscript and then on the front to do 4, but then on the other side you have
Okay. Believe it or not, this is not diatomic hydrogen. See, a lot of people every year on the test they say, "My eye saw H2." No. That's not true. Here's what it is. It's HHO. I don't see any diatomic. You see any diatomic hydrogen in there? I don't. Just because your eye saw a little 2 down there, that's not. By the way, this is not hydrogen. It's called water. What's this called? That is hydrogen. That is diatomic. That's not diatomic hydrogen. It's HHO. Same thing yesterday. See this right here? Zinc chloride. What is that? That's zinc. Is that diatomic chlorine? No. It's one of those and 2 of those. I'll draw it for you. There's one of these guys, and he's what's clinging on to him? 2 of these guys. What? See? There's no diatomic chlorine there. That's a good question you had though. Every year people do that because their eyes saw H2. They write H2 here, and it's not diatomic hydrogen there. Okay, what do you think? Now, I want to tell you one more thing, and if you are reading the book, you're supposed to. It's not that difficult, but one statement, a very fast statement. Here we go. what if I ask you on this question here, who got oxidized? Who got oxidized in this reaction? Which one? Zinc. Isn't it right? Who got reduced? Hydrogen. Now, if you've done any of your homework, one of the questions I might have asked was, who was the oxidizing agent? What? Who was the oxidizing agent? Who was the chemical that caused somebody else to be oxidized? And watch what happens here. Guess what? Who got oxidized? Zinc. Who was the oxidizing agent? Who was it that caused zinc to get oxidized? The thing that got reduced. Who was the reducing agent? What? The reducing agent. The one who caused somebody else to get reduced. Zinc. If you got oxidized, you were the reducing agent. If you got reduced, you're the reason somebody else got oxidized. That's a minor thing. I know it makes your brain twist a little bit, but it's not that hard. Okay, that's pretty much it, except for the last thing I want to show you. And this lesson, it's a very short lesson. I know you can get it. Every year I do this, and every year people get almost every one of these questions right. They should get all right. So I'll take back one of those. Take one. Okay, this is not in the book. It's not in the book. Matter of fact, you'll like seeing these on the test because you'll say, that I do understand. So let's see if I can get there here. The reason I have to teach it to you because the nice big lab I have get it ready set up for you next week. The lab we have ready for you, there's one more component that I need you to know about before you can understand all the different reactions you're going to do. You can put the rest of them over there. Okay. This graph is found in almost every biology book and chemistry book. I don't think Miss Founds did that in the 9th grade, if I had to guess. Is that correct? Have you seen this? Okay. All right. So let me show you this. It's not as complicated as you think it is. All right. Reactants, right? So let's say you have some things that are going to react. If you don't like the 3 balls and make some squares or something like that. Okay. What if I told you that the total amount of energy in the reactants was some number, and I'm going to make up a number. You know what? I like 50. I like 50. Hey, where'd you get the 50? I made it up. I just said 50. I hereby declare that all the chemicals that are going to react have a total amount of energy of 50. Okay, I got you. Now, this says reaction progress. That's like time, isn't it? And what's down here? Product or products, right? Now, I hereby declare that that number is 25. I just made it up, didn't I? I just made it up. So let me ask you this. What would happen if you had reactants that had an energy level of 50, and I just made that 50 up, didn't I? Just made it up. Whoa. I'm going to tell you another reason why some chemical reactions take place, right? So the reactants have an energy level of 50, like $50. But when they get done reacting, it's like, how much are you worth now? 25? And anybody, even if you're not a chemistry person, would say, what if your parents, you went to school with $50, and you came back with 25? What would they ask you? Where's that 25? Where's that $25? And what would a chemist ask? Where's that 25 units of energy? Where'd it go? Where'd it go? I started at 50. What? Anybody have any ideas? What do you call a reaction that gives off energy? I know you had this in biology. What do you call it if you know that it gives off energy? So 25 units of energy were given off, right? And if I was in a test tube, it would make the test tube hot. Anybody know? I know you did this in biology. Exo what? Thermic. Now, exothermic, you had it, didn't you? Yes? Where you put two chemicals together and it gets hot, and energy is given off. It's called exothermic. I don't know if you've ever been away from the school where we have an ice machine here, but if you're away from the school and something happens to your ankle and they want to put an ice pack on it, they might not have ice. Maybe the concession stand's not open. They have this little bag, and you crush it. You crush the bag, and that makes one chemical react to another chemical, and all of a sudden that bag gets really, really cold. What's that called? It's not giving off energy, it's doing what? It's taking in energy. What's that? What kind of reaction is that? Endothermic. Remember those? Okay, now, as you stay in science, some people figured out, you know how there's political correctness? Well, sometimes there's scientific correctness. Exothermic was used forever and ever and ever, and then somebody said, wait, some of the reactions, it's not heat that they give off light. Yeah. Therm means heat. So you got to stop calling it exothermic. And some energy might be another kind of energy. So they say exergonic. Exergonic. Have you ever seen that word? Okay, it's the same thing. Exergonic, exothermic, okay? All right, now, the reason I want to show this to you, all right, is that sometimes you'll put two chemicals together and they will spontaneously react. When I put sodium in water, did I have to heat that up? No, it spontaneously react. But there are some reactions, you're going to do one of those. You're going to do a reaction in the lab where you want these chemicals to react, but they won't. They're just sitting next to each other, they won't. So we have to heat them. We heat them. And when you heat them, they start running into each other with more energy, and then they'll react. You get it? So we have a name for that, and that's called activation energy. Activation energy. And that's the energy you have to put in, and guess what happens? They're sitting next to each other, and they're not reacting, and I heat them. Now they're moving, and then they get to a certain speed, they run into each other, boom, boom, and then they turn into the products. And I know that the products had less energy than the reactants, so it must have given off energy. So I put energy in to heat them up. I got that energy back, and I lost more. You see that? I lost that amount of energy plus more. And so the bottom line is, if you start at 100 and end at 25, you lost 25 units of energy. Now, activation energy required for a chemical reaction, and said some of them you do have to heat, and you're going to do that. I have one here. You're going to do copper. Hey, copper, I want you to react with oxygen in the air. So you sit there and you watch it, and you watch it, and you watch it, and you say nothing. And then you actually read the directions. And they said, put the copper in the Bunsen burner. Oh, okay. Now, why would I have to do that? Why do I have to heat the copper? Why didn't the copper just react with oxygen right now? Again, they're not energetic enough. But if I heat them, now they run into oxygen. Now a reaction will take place. Okay, so that's the main story. One of the driving forces of reaction is that a lot of chemicals like to take on the lower amount of energy. I never understood this, but dynamite, for example. Dynamite is a chemical that has a lot of energy in the bonds, a lot. But when you light it, when you explode it, it turns into something like nitrogen, simple nitrogen gas. And so you take this thing that has a lot of energy, and when you heat it or explode it, it says, woo, I want to turn into this guy with almost no energy. Oh, yeah? Well, what happened to all the energy that you used to have? Ba-boom. I released it. When I release that energy and it heats the air around me very quickly, boom, 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 then it sets up a shock wave of air, and that's what blows down buildings. And so one of the one of the driving forces is that things like to lose energy become more stable. Now, why am I showing this picture, okay? And you're going to have a lab here where there's this one chemical that you want to decompose. And you watch it and you said, do it. And it won't. It won't do it. And so what I'm going to do is I'm going to show you this next picture, okay? And the next picture has to do with this word here. It's called a catalyst. Did you guys, I know you had to say the word catalyst in biology class, didn't you? An enzyme is a chemical that what? What does a catalyst do? It speeds up a reaction or makes it happen when it maybe wasn't going to happen, but it itself is not destroyed. It can do it again and again. If you have an enzyme, do you know what sucrose is? Os means sugar, right? Sucrose is the sugar in your home. If I put sucrose in my mouth, there might be an enzyme called sucrase. And sucrase is an enzyme. I'll say, oh yeah, I'll break you apart. Yeah, there's another one, I'll break you apart. Boom, boom, boom. And the sucrase didn't change at all. The catalyst didn't change at all. But it caused sucrose to be broken down. And those are called those are called catalysts. So let me show you the little drawing here. Ready? How much energy did the reactant start with again? We're just making that number up. How much did it start with? 50. I made it up. And how much did it end up with? 25. I made that number up. Is this still going to be an exothermic reaction? If you start at 50 and you end up at 25, you're still going to give off, it's still going to be exothermic, isn't it? Okay, we got that. Now, what's different about this drawing than that one? And look right here. Here, I had to have a lot of activation energy. See that? A lot. Just to get him to react. Well, what happened here? What happened here? And the theory is that what does a catalyst do? A catalyst allows the reaction to take place faster because what does it do? It reduces the what? It reduces, what is it? It reduces, help me out, a catalyst reduces the what? The amount of activation. So no wonder it makes the reaction take place more frequently, more quickly. And there are people all over the world, I know you don't believe this, but all these chemical people that are making things, if you can develop a catalyst and that company says, hey, we can make this many thousands of gallons of this chemical a day. And you have a new process where a catalyst will make it happen faster. Now we can make 10,000 gallons per day. Do you think you might get a raise? If you develop a catalyst that makes that reaction take place 10 times faster, you think that company might outcompete another company who can't make it that fast? And so catalysts is they're a really big idea, and they lower the amount of activation energy. Okay. All right, so here we go. Question number 1. Let's see if you understand the lesson. The lesson's done. A catalyst speeds up the rate of a chemical reaction by blanking the amount of blank. If you understand the lesson, fill that in. You say, whoa, I think I understand that lesson. What do you have? Who wants to answer that? Ooh. Yes, Noah.
By reducing the amount of activation.
Excellent. Reducing the amount of activation energy rate. If the products have less energy than the reactants, where'd the missing energy go? Who wants to answer that one? Max.
It's given off during the reaction.
Yes, it's given off. And we can say it's exothermic, can't we? Is this making sense to you? This is a lot easier than the redox, isn't it? All right, next, number 3. Is the above reaction endergonic or exergonic? And again, all the new books are using, instead of exothermic, they're using exergonic, okay? Is it endothermic or exothermic? it's, you said it was given off, right? So it's exothermic, exergonic. What would the graph of the other choice from above look like? What if it was actually endothermic? You know what X means? Like exit? Exit means out. Exit means out. Exothermic means you give off, it gives on out. Hey, what would it be? Can you do that? Try that. This is the hardest question so far. What would a graph look like of endothermic? You go to school. You go to school with $50. You come back with what? You come back with 75. What are your parents going to say now? They don't going to say where you lost $25. What are they going to say? How'd you take in an extra $25? So all I have to do is have the products up here, don't I? Now, if you thought the reaction could take place just like this, you could draw it like that, but it's possible you still might have needed some activation energy and still ended up like that. It could have been like that, you get that? But if you drew anything that looked like, if you had the products here and the reactants here, then you know that's that. And maybe for the first time, this might make sense to you. Look right here. Do you remember this at all from biology? Do you remember this at all? Can you tell me what that is? Okay, do you know what this was? What'd you call that in biology class? It is food, but what? Glucose. That was glucose, right? And this is oxygen. And so what happens if I'm in a coma, and they said, well, if you stay in a coma for a long time, your body's going to need energy. Now, do they, at night, do they put a Big Mac in my mouth and go like this? Is that how they feed me? I'm in a coma. They'll choke me, right? No, so how do they feed me? They put a tube in my arm. What's they have in there? Glucose. They call it dextrose in the hospital. So they put this simple sugar in there, and the simple sugar goes all over my body, and it's got this in it. And all the cells said, oh, I'll take that. I'll take that. And where, do you know where this happens in the cell? There was a name for that in biology. I know you did it. It was called cellular respiration. Oh. And what you were doing is you were taking food that had energy in it, and what were you doing? What was that, Krebs cycle? What was that? Did you ever have the Krebs cycle? Wasn't that where you took energy? You took something that had energy and said, hey, God said, if I release all the energy all at once, it'll burn the cell up. I better make a really complicated thing that takes a little bit of energy out, a little bit of energy out, a little bit more, and I'll even store some of that energy in ATPs. Oh, that's what that meant? Yeah. And so what you did is you took something high energy and you combined with oxygen. You wanted to become something that was lower energy. It gave off energy. Instead of burning up the cell, I think I'll trap some of energy in ATPs. And even when you're not eating, you can have some ATPs later if you want. Okay. What about photosynthesis? Whoa. Photosynthesis. See? Photosynthesis takes up almost no energy. You end up with something that has... How'd you do that? He took in energy, didn't he? Okay, well, I'm done. If you can have the rest of the period, if you want to work on your homework, I have the homework here. If anybody, even at lunchtime, if you want to come in and look at the answer key, you can do that. But I need to stay in the room, but if you can, whatever you need to do to study,